Alright, you're welcome to SK Pass College. If you have not yet subscribed to this channel, I will urge you to subscribe to the channel, like the video, and share to other colleagues. Today we are going to discuss hybridization and bonding. If you have not watched my previous videos on hybridization or chemical bonding, you can search SK Pass College and watch this video before you come to hybridization. Okay, so basically, what do we mean by hybridization? So let's discuss everything about hybridization. When you say hybridization, it is just the mixing of two or more orbitals. So let me write it here. So when we talk about hybridization, we are going to discuss a lot about shapes. Okay, so hybridization is just the mixing of two or more atomic orbitals with different energy and shape to form new hybrid orbitals with an equivalent energy and shape. So the emphasis is on the fact that anytime we are doing hybridization, we are mixing two or more, okay, two or more atomic orbitals. So we shall look at what we mean by atomic orbitals. And when we say atomic orbitals, we are referring to an atom. Atomic orbital or an orbital is a volume of space in which there is a higher possibility of finding an electron. When we say an orbital, it is the volume of space in which there is a higher possibility or a higher probability of finding an electron. So what it means is that when you pick the orbitals, we have the S orbital, we have the P orbital, we have the D orbital, we have the F orbital. These are the main orbitals we are going to mix. So in hybridization, when you pick any of these orbitals, you mix them, they come out with their shapes. And so the new shapes form is what we term hybridization or hybrid orbitals. The new shape form is the hybrid orbital. Having said this, what it implies is that in this hybridization, someone asks what is the main essence of studying hybridization. We have so many applications of hybridization, so by the end of the lesson, we shall discuss basically the importance or the reasons why we need to study hybridization. But before we move on, we are going to discuss some types of hybridization. But I have to say that when we pick hybridization, there is a concept you need to understand. It normally occurs in covalent molecules. Hybridization occurs in covalent molecules. What it implies is that you cannot pick something like an ionic compound whereby you want to find its hybridization. So we need to understand that this hybridization we are coming to discuss, basically, when you have watched my previous videos on bonding, you understand what we call covalent bonding, metallic bonding, ionic bonding, and all that. And we have to lay emphasis on the fact that this hybridization we are coming to discuss basically takes place in covalent molecules. But however, it is not all the covalent molecules that hybridization occur. And so when we study further, we will realize the main types of covalent molecules that hybridization can occur. That will lead us to a concept called sigma and pi bonds. These are special hybridization or covalent molecules that undergoes hybridization. So having said this, let's now talk about the types of hybridization. My black marker is not helping, so I'll switch to red. So before we move on to the types of hybridization, we have to know some few things about these orbitals. For instance, when you pick the s orbital, for instance, we know that this s orbital is spherical in shape. So the shape of this s orbital is spherical in shape. So we need to have that concept, but we are going to build on this concept. Now, when you pick something like the p orbital, the p orbital is dumbbell in shape. And this p orbital is a degenerate orbital. This p orbital is a degenerate orbital. Now, what do you mean, or what do you mean by a degenerate orbital? A degenerate orbital is an orbital which have the same energy level but different orientation or different directions. A degenerate orbital is an orbital with the same energy level but different orientation or direction. So what do we imply, what do we understand by this degenerate orbital? For instance, when you pick the p orbital, it is a degenerate orbital with three subdivisions. We have the px, py, and then the pz. This orbital, they all have the same energy level, meaning the energy level here is the same as the energy level here, is the same as the energy level here. But in terms of direction or orientation in space, they have different orientation in space. So let me fold them, fill this singly, and pair them. So these have been fully filled with 6 electrons. With this orbital, this is what we are going to talk about. On the Cartesian plane, we have this as our x-axis, or the abscissa, and then we have this as our y-axis, or the ordinate. But because this has px, py, pz, we prefer to name it systematically in that order. So we are going to have this as our px. There is in between this and that, there is another orientation, which we call the py. So this is, since we say p orbital is number, this is the shape. So this is the shape of px orbital, and this is the orientation or the direction. Now we can have a different location here, and so this will be named as the y. So this is our y. So this becomes our py, and then this becomes our z. So the z is here like this. So these are the 3 directions or orientations of this p orbital. Although they have the same energy level, but their directions are not the same in space. So this is px, py, and pz. We are going to make very good use of these orientations when it comes to hybridization. Having said that, quickly, since we know the s orbital is spherical in shape, we are now going to look at the types of hybridization. Now there are so many types of hybridization, but in this video, we are going to focus on about 4 or 5 of them. So let's look at the types of hybridization. So we are going to focus. There are so many types. You can get the other types. We are going to have discuss sp hybridization, sp2 hybridization, sp3 hybridization, sp3d hybridization, and sp3d2 hybridization. So these are the various types of hybridization we are going to discuss. So having said that, let's plan and then discuss the first type, which is sp. Alright, now when we say sp hybridization, there is something we need to understand. We need to know what we call, there are some bond parameters that we have to be familiar with. When we talk of bond parameters, we are referring to bond length, bond angle, okay, and other stuff. So these are some bond parameters you have to be familiar with. We will look at the difference between a shape and a geometry in this presentation. And this hybridization will help us to predict some molecules, the shape of some molecules, which we are going to use a concept. So you have to continue watching the video to the end. We shall use a concept known as the Vesper theory. It's a very nice theory, and we are going to look at some other theories like molecular orbital theory. So let's discuss everything on sp hybridization. Alright. Now, anytime you hear the word sp hybridization, the first thing that must come into your mind is that this sp hybridization, in terms of bond parameter, the bond that exists between this sp hybridization is a triple bond. A triple bond. So, when I want to use carbon-carbon to illustrate this, it means that we are going to have something like this. So this is a triple bond. And when you have a triple bond like this, what it implies is that there are some, I told you that hybridization occurs in covalent molecules. And not all types of covalent molecules, but specifically we have some specific covalent molecules that occurs. These are the type of covalent molecules occurring here. We have a sigma bond and pi bonds. So we have one sigma bond with two pi bonds. So basically that is what we need to understand. This is one sigma bond with two pi bonds. So this is sp hybridization. So let's discuss this into details. How do I explain sp hybridization? So just the name predicts or tells us exactly what you are going to form. sp hybridization is a type of hybridization that occurs when an s orbital is mixed with a p orbital to form two hybrid orbitals. So in sp hybridization, it is just the mixing. So it is So sp hybridization is the mixing of an s orbital, so this is the s orbital, with a p orbital. And anytime you mix an s orbital with a p orbital, two hybrid orbitals are formed. So the question is, how many hybrid orbitals are formed under sp hybridization? The answer is 2. Anytime there is an sp hybridization, two hybrid orbitals are formed. So how do we form that? Let's look at how it is formed. So what we are trying to see is how do we mix this s and the p orbital? Now we know that the s orbital is spherical in shape. So this is s orbital. I'm mixing this. So I'm going to use different markers so that we see the difference well. I'm mixing this with a p orbital, we know the p orbital is that dot in shape. So this p orbital, we are just missing one of them. And we know that the p orbital, we have ps, py, and pc. So we are just missing the px. So that's how I represented that. Just one of them. So you can see, when we are preparing granite soup, we need some ingredients. You have granite, tomatoes, you have maybe your meat and other ingredients. So when you are mixing them, you mix them differently, but by the time the food is ready, you are not able to distinguish between the granite and then the water and all that. They mix completely. So that is what happens here. I'm mixing this with this. Now, anytime this is done, I form two hybrid orbitals, but this time around, as soon as I mix them, you are not able to distinguish this from that. You cannot distinguish again. So what will happen is, I'm going to form this. So you can see, they are the same energy and shape. Okay, so look at this. This is the hybrid orbital form. After mixing this and this, I form this. You cannot distinguish between these and that. You cannot tell me this is S and this is P, but I've mixed these two. And I'm able to form these two hybrid orbitals. So that is how sp hybridization occurs. So when you mix the S and the P, you form two hybrid orbitals. Now, there is something we need to know about this. Anytime you are discussing something on sp hybridization, you need to know all the features of this sp hybridization. The question they can ask you is, what is the shape of the sp hybrid orbitals? Or how do you predict easily that sp hybrid orbital? What would be the shape of that orbital? Or any molecule having sp hybridization? The question or the answer is, look at this. This is on a straight line like this, because they prefer, when they are forming, you cannot form them like this, like another one. You cannot form them like this. They prefer to stay far away from each other. And that one will come to that. There's a concept on that, which we call the Vesper theory. So valence, there's a repulsion. So we'll come there. But whenever you are representing this, they should stay far away from each other. So this will be the shape. And this shape is in a straight line. So we can say that sp hybrid orbitals are linear in shape. So that's another point. The shape, their shape, it is linear. So this is the shape of all sp hybrid orbitals. They are linear in shape, as a straight line. So there is another thing we need to know. If you have a straight line like this, in terms of angle, what is the bond angle of sp hybrid orbitals? So angles on a straight line sum up to 180 degrees. On that note, we can also say that sp hybrid orbitals, they have a bond angle of 180 degrees. So these are the basic things you'll be asked or you'll be requested of: the shape, the number of hybrid orbitals, and the bond angle. So it is linear in shape, it has two hybrid orbitals, and the bond angle is 180 degrees. So having said all this, let's take a typical example of an sp hybrid orbitals and explain the concept better. For instance, let's take beryllium chloride for instance. So if you want to determine the type of hybridization in a molecule, the first thing you do is to look out for the central atom. Now what do you mean by a central atom? On the periodic table, we have the s orbitals, the p orbitals, the d orbitals, and the f orbital. The s orbitals, they are the solid or the metals. Okay, then we have the p orbitals. When you are moving from left to right, you will be moving from metallic to a non-metallic property of elements. So with this one, the central atom is the most electropositive element among your molecule region. So when you pick beryllium and chlorine, the question is, which of these two elements will be the most electropositive element? And the answer is, come, pause your video and drop your answer in the comment section. So beryllium and chlorine, which one is the most electropositive element? I get it right. So the most electropositive element here is beryllium. And we know beryllium has atomic number 4. So on that note, we are going to write the electronic configuration of this element using the SPD notation. So quickly, let's write. We have 1s2, 2s2. Since this is having atomic number 4, this 2 plus 4. One thing we need to note is that in chemical bonding, specifically hybridization, when you are mixing or in chemical bond, we only use the valence electrons. They are the only ones that undergo chemical bonding. We do not use core electrons. So when you look at this electronic configuration we have written is what we call the ground state. The ground state electronic configuration. But because we want to follow the rule whereby we don't use core electrons and we use only valence electrons, then we have to rewrite this electronic configuration in an excitation. That's what we call excited state. What do you mean by excited state? Excited state is a situation whereby you promote an electron from one energy level to the other. Okay, so in this case, we are going to rewrite this, and this one will not appear because this is a 4 electron. So we only deal with the 2s. So this beryllium, we are going to deal with only the 2s2. And when you are writing this 2s2, excuse me, 2s, we want to write it in the detailed form. So we know we are going to have these 2 electrons, and this is the outermost electron. So this is the only one that will have to undergo the chemical bonding. But the question is, when you want to undergo chemical bonding, when you have 2 electrons like this, it means you cannot bond with other electrons. You cannot go for another electron to be 3 because there's a rule governing this, that the maximum electron this can pick is 2, and they should be in the opposite spin like this. So what it implies that for you to mix this with another orbital, you need to promote this electron to a higher energy level. So from 2s, we move on to what? 2p. So this p orbital, we know is a degenerate orbital. Like this. So what is going to happen is, we are going to promote this electron here. So in actual sense, this is now behaving like this. So this is what we are getting. These are empty orbitals. And so we have 2s1 and 2px1. So this is called an excited state. This is the excited state electronic configuration. In this case, we cannot mix 2 of these orbitals because we said in sp hybridization, we mix 1s with 1p orbital. That is the meaning of sp. So what will happen is we are going to mix these 2 orbitals together like this. Okay? So I want to give us a better clarification on this. This is our beryllium. Now with this beryllium, it has formed 2 hybrid orbitals because we know when you mix these 2 orbitals, you cannot observe them like this is S and P. They behave separately. So we are going to have something like this. This is 1, and then this is another one like this. So these are hybrid orbitals. These are the 2 hybrid orbitals as a result of mixing these 2. Now when you mix them, this beryllium is bonded to some element or chlorine. And so the question is, you have to ask yourself, chlorine on the periodic table, is it in the S block or in the P block? And so you should know that if chlorine is in the S block, then the shape of chlorine will be spherical. But that one, you have not mixed it. It's just being attached to the beryllium or the central atom. So the question is, chlorine on the periodic table, we know chlorine belongs to group 7. Or in the modern periodic chemistry, we say it is in group 17. So with that, we can see clearly that it is in the P block. And all P block elements are down beryllium. So what it implies is that chlorine will have to come and attach itself to this, like this. This is down beryllium. This is one chlorine. And this is another chlorine. So this is how we represent it. This is a chlorine. This is chlorine. You can see something clearly here, that the whole molecule is in a linear state. That is why we say this type of hybridization here is linear in shape. So what happened here is like this. This beryllium donated one, and then chlorine also donated one. They will share to form a covalent molecule here. This beryllium at the central atom will donate one electron. This chlorine will also donate one. They share to form a covalent molecule. And so what you are saying, this is the actual shape of beryllium chloride. This is the actual shape. And this is what we refer to as hybridization. You can see clearly that the shape you are seeing is linear in shape. And therefore, if you want to simplify this better, you want to get a clearer view of this. This is how to see beryllium chloride. So what has been formed here is a bond. When they share, they form a bond. So anytime you see this line, you can watch my previous videos on chemical bonding. You will understand the concept better. So anytime they share like this, they form a bond like this. So this is beryllium, and there's a chlorine. Okay? And then this is another bond. And so there's a chlorine. Okay? So this is what you are saying. If you have studied chemical bonding, you realize that there are some of these. Let me indicate this on that so that you get the concept better. There are lone pairs on it like this. Okay. So this is the structure or the shape of beryllium chloride. Very nice shape. So any question that you can ask on this, beryllium chloride, is it ionic or covalent? The answer is beryllium chloride is a covalent molecule, because we said that this is going to undergo a hybridization. So it's a covalent molecule. So what type of covalency is there? This falls under what? An sp hybridization. There is another super trick that I'll use to teach simple ways of knowing the type of hybridization in molecules. Maybe not in this video, but in my next presentation. So this is basically everything about. You can try more examples on sp hybridization. So this is sp hybridization, basically. Alright, let's look at the next type of hybridization. Okay, so with the next type of hybridization, we are going to talk about sp2 sp2 hybridization. So just like we did for the first type, you have the concept now, so it's not going to be difficult. So what is it sp2? There are basic questions that we'll ask. The first basic question is, what is the type of hybridization? What is the shape of this sp hybridization? What is the bond angle? So let's look at them. How do you also explain this sp2 hybridization? It is also the mixing of an s orbital. So you can see sp2. It is the mixing of an s orbital with two p orbitals to form three hybrid orbitals. So the question is, how many hybrid orbitals are formed under sp2 hybridization? Okay, and the answer is it forms three hybrid orbitals. Very, very simple. Now, if that is the case, we would like to know the bond angle and then the shape. But before we do that, let's look at how this is mixed. Since we are mixing an s orbital with two p orbitals, it's going to be like this. Let's look at how the mixing is done. This is an s orbital, spherical in shape. Okay, plus the p orbitals, we know we have two of them. We have, this is px. Okay, we know that y is like this. So we have something like this. This is py. So we are going to mix these three. Okay. So let me draw this for. This is like this, but this is split. So px. So we are mixing an s orbital with these two p orbitals to form three hybrid orbitals. So in these hybrid orbitals, they prefer to stay far away from each other. Look at the arrangement. They prefer to stay far away from. So look at this. This is like this. One is staying here. Far away from here is another one here. Far away from here is another one here. So this is how they look at it. So when you look at this, in geometry, mathematics, you can see the pictorial view of this. It's like this. I want to look at this. So when the thing is like this, anytime you have something like this, okay, that's how it's looking like. So it's like this. Geometry, so I'll show you. So this is how it looks like. So this is a triangle, and so we have this shape as a trigonal planar. Trigonal planar. So look at this. So this is a trigonal shape. I'm going to indicate the shape. So this is the shape of this sp2 hybrid orbitals. There is a difference between geometry and shape. When you are doing Vespa theory, I will lay emphasis on the difference between. They have some similarity. They are not the same. So this is the shape. Shape you see is a trigonal planar. So for all sp2 hybrid orbitals, the shape of these sp2 hybrid orbitals are trigonal planars. So someone will ask, then what do you think will be the bond angle? So the bond angle here is going to be 120 degrees. So you see, when we did for SP hybridization, we had a bond angle of 180. This time around, the bond angle here is 120 degrees. So these are the basic things you need to know about sp2 hybridization. Now, in terms of the bond here, just like using the carbon-carbon, it's going to be like this. So this is how it will be like. Okay. So this is how it will be like. It's having a double bond. So the bond existing between these sp2 hybrid orbitals is a double bond. Okay, double bond in a sense it is having one sigma bond, and a pi bond. So that is what you need to know. All right, now basically let's look at how we can also form example of a molecule H16 or having sp2 hybridization. So there are so many examples. I'm just working on one example. So you can get more examples, you work and get the concept better. So let's look at an example like PF3. Okay. PF3. The first thing you need to ask yourself, just like we said, is, what is the central atom? I've explained the central atom. Central atom is the most positive element. So between boron and fluorine, we know boron will have the central atom. And boron has atomic number 5. So we have to write 8 electronic configuration. In the ground state, 1s2, 2s2, and so 2p1. So this is 5. And this 2p1 is the 2px1. So this state of configuration is what we call the ground state. Now let's excite the electrons. Let's excite the electrons. We have said that in chemical bonding, we don't use the outermost electron, we use only the valence electrons. Now when you come here, what is the valence electron here? This is 1s2, 2s2, 2p1. Here, don't say the valence electron is 2p1. No. This is the valence electron. 2s2, 2p1. Why? Because they have the same principal control numbers. So you cannot just use only one. So this is 2s2, 2p1. So we are going to represent that in the SPB notation like this. So this is 2s, that's 2 electrons, and this is the p. That's only one. So if we want to write it in the ground state, I've explained that in the ground state, we excite the electrons. We promote, because this one cannot be bonded to other, because it has only 2 electrons already. We need to have one so that it can bond with another person before the hybridization can occur. So because this is having 2, it must be promoted. So this electron will be promoted from here to here. So in doing that, this is what it will form. We have promoted one here, so we are left with only 1 electron here. And this is our p orbital. This one is already here. This is what we have promoted, so this will come here like this. So we have 2s, 2px1, 2pz, 2py1, and then 2pz0. This is an empty orbital. So this is what we call the excited state. This is the excited state configuration. Now, for us to form something meaningful, now we are going to mix. We said sp2. sp2 means you are mixing one s with 2 p orbitals. So this is one s with 2 p orbitals. So we are going to mix the whole of this. So when you mix that, this is what we get. This is our boron. Okay. When you mix them, you form hybrid orbitals. You don't differentiate between this and that. So they form something like this. So this is the first. See, they stay far away from each other. Okay, like this. They stay far away from each other. Because the bond angle from here to here is 120. You don't have to bring it so close to this. They stay far away from each other. So let me redraw it. Stay far away from each other. Okay, so this is what we have formed. And this is the 3 hybrid orbitals formed. Now, the question is, this is our central atom. These are the 3 hybrid orbitals. This boron is bonded to fluorine. So quickly go and check. Fluorine itself, which block is this fluorine? Is it on the S, P, D, F block? So when you check on your periodic table, you realize that fluorine is in group 17 according to the modern periodic table, or group 7. So you know definitely that fluorine is a P block element. So this, you bring the actual shape, and the p orbitals are amniotic. So this is what we are going to form. Let me use a different color. This is the P, this is 1. This is another one. This is the third one. So what you are seeing in there, these are the fluorines. This is fluorine, this is fluorine, this is fluorine. So what will happen here is, this will donate one, boron will donate one, fluorine will also donate one. They share to form a covalent molecule here. So that is how the sharing is done. Boron will bring one, electron donate one, fluorine will also donate one. They share to form a covalent molecule. Boron will donate one, fluorine will also donate one. They share to form another covalent molecule. So in actual sense, this is the actual shape of boron fluoride. This is the actual shape. And the type of hybridization in there is an sp2 hybridization. And the bond angle there is 120 degrees. So the bond from here to here is 120 degrees. And the shape of this, you can see the shape clearly. This is a triangular plane, it's a triangle. You can see that. And you give a pictorial view of this. You can see this is a triangular plane. It's a plane and bias. You can see this clearly that this is a plane. So this is a triangular plane. So that is the shape. We want to simplify this. This boron is like this. Bonded with, you see, when they form a covalent bond, this is a line. So this is fluorine. This is another fluorine. This is another fluorine. So this is the simplified way. And these ones, they also have lone pairs. Let me indicate the lone pairs on it. Fluorine is electronegative. You know on the periodic table, fluorine is very electronegative. The most electronegative element on the periodic table, fluorine. 2.6 here. There's nothing here. So this is very good. So this is another one. Okay. So this is the simplified diagram of boron fluoride. And this is the type of hybridization, sp2 hybridization. There are more examples, so you can get, I will give you a work example of some of the molecules and how to write them. You can try your hands on some of these. Alright, so let's move on to, I want to exhaust the types of hybridization so that in our next presentation, we focus on other stuff. So let's look at to the next type of hybridization, which is sp3 hybridization. I will not waste time on this. I will just explain some few concepts, just like we have done for sp2. When you say sp3, it is the mixing of an s orbital with 3 p orbitals to form 4 hybrid orbitals. So when you mix an s orbital with 3 of the p orbitals, how many hybrid orbitals are formed? 4 hybrid orbitals are formed. Okay, 4 hybrid orbitals. So that is one concept. So when you ask to explain sp3 hybridization, it is the mixing of an s orbital with 3 p orbitals to form 4 hybrid orbitals. Alright. Now, in terms of carbon-carbon bonding, when I have a carbon-carbon, we have carbon. So this is a single bond. Okay, so we did for sp, we said it's a triple bond, sp2. So this one is a single bond, like this. In between the carbon-carbon, it's a single bond. So it has only a sigma bond. There are no pi bonds here. Alright, so having said this, quickly, so the single bond, the bond existing here is a single bond. That of the one existing in sp hybridization is a triple bond, sp2 is a double bond. Alright. Now let's come to the shape and then the angle. In terms of shape, let's meet this S. This is spherical in shape. So this is the S of the spherical in shape plus P, 3P. So we have Px like this, Py like this, and Pz like this. This one is dismantled like this. So Px, Py, Pz. When you mix them, you form 400 orbitals. So this is what happens. They prefer to stay far away from each other. So this is what happens. Okay. So this is what happens. And so the shape of this is what you call this shape. So this is tetrahedral in shape. Shape of this is tetrahedral. And the bond angle from here to here is 109.5 degrees. The bond angle for sp3 or sp3 hybrid orbitals is 109.5 degrees. So basically, these are the things you need to know. It forms 4 hybrid orbitals, bond angle of 109.5, and then the shape is tetrahedral. Let's look at a typical example how this sp3 hybridization is also formed. So let's see a typical example, just like we did for the others. Here, we will not waste time. I've explained a lot of concepts on these already. So, the typical example I will use is methane, CH4, methane. So, with methane, first of all, I have to pick the central atom, which is carbon, atomic number 6. 1s2, 2s2, then 2p2. So, this is the ground state electronic configuration. The ground state. Now let's excite this. We said that we don't use the core electrons, so we are going to concentrate on the outermost electrons, which we call the valence electrons. So these ones. So we have this 2s, then 2p is a degenerate orbital. We have 2 of the electrons here like this. This is a different marker. We have 2 of the electrons here like this, and this one has also 2 electrons like this. Now, this is having 2, it cannot undergo the chemical body and the mixing because it's having only 2, already 2. So you have to promote an electron from this lower energy to this higher energy. So we are going to excite, promote an electron from here to here. Okay? So when you do that, this is what you get. 2s is left with only 1 now. There are 2 electrons here, and then the one promoted is also here. So all the 3 orbitals are having single electrons. So this is Ps, Py, Pz. Px, Py, Pz. They are all having 1, 1, 1. So we are going to mix, what is it? sp3 is mixing an s orbital with 3p orbital. So we are going to mix all this time around. So let's look at how the presentation goes. This is my carbon. That's 4 hybrid orbitals. So these are the 4 hybrid orbitals. One comes here like this. Comes here like this. One comes here like this. And the next one comes here like this. So these are the 4 hybrid orbitals. So now, having formed these 4 hybrid orbitals, we have to note that these hybrid orbitals are bonded to hydrogen. Hydrogen is having, and so you have to know the shape of hydrogen on the periodic table. So that's why in chemistry, you don't do away with periodic chemistry or periodic table. So it is very important that anytime you are doing chemistry, you have to have your chemistry table or the periodic table before you. So if you don't have one, grab one. You can go online and print one. There are so many versions. Bring the standardized ones and use for your lessons. So here, you realize that when you check on the periodic table, hydrogen is in the S block. So S blocks are spherical in shape. So here, you are not going to use the dumbbells you are using. You are using dumbbell because they were on a clip. This time around, you are going to use spherical. So the hydrogen is spherical. So this, I'm going to use a different marker. This is how this is spherical. So that there are four. They are spherical in shape. So this is how they will be. And these four will donate an electron each. And carbon also donate one. So this one will donate one, this one will donate one. They share to form a covalent bond. They share to form a covalent bond. Share to form a covalent bond. They share to form a covalent bond. So what we are seeing here, they are the hydrogen. They are the hydrogens. This is hydrogen, another hydrogen, another hydrogen. So this is the shape of methane. See, that is the shape of methane. If you want to simplify it just like we did for the others, I want to simplify this. This is our carbon. Okay, so this one forms a covalent molecule like this. So this is our methane. Okay, so this is tetrahedral in shape. You can try more examples on your own. Now, I don't want the video to be too lengthy, so I want to talk about maybe probably the last two. I'll summarize it. I'll just talk about one. The last one I'll give it to you as an assignment to try your hands on it, and you come out with your solution if you don't understand anything. So let's look at, there's another one. Don't understand anything, you can write it in the comment section. If you want clarity on anything, you can write at the comment section. So let's look at sp3d hybridization. And then we have sp3d2. That one I'll give it to you as an assignment. But when I finish with sp3d, you can easily do the sp3d2. So with this sp3d2, it is also the mixing of an s orbital with 3p orbitals with a d orbital. So it's very simple. Mix an s orbital with 3p orbitals with d orbitals. So in this case, how many hybrid orbitals are going to form? This is 1 plus 3 plus 1. So we are going to form 5 hybrid orbitals. 5 hybrid orbitals. So I'm missing an s orbital. So I'm not going to go through all the steps I did. But what you have to understand is that when you mix this s with 3p with d, you form 5 hybrid orbitals. You can do the presentation. But the question is, how are these 5 hybrid orbitals formed? This is how it is formed. So let's assume I have my central atom. First of all, it will form something like a triangle. Okay? So like this. When this is formed at the equator, the equatorial level, there are 2 other forms like this, formed like this, like this. So this is how the 5 hybrid orbitals are formed. And this one, you can see from here, it forms something like a pyramid. So you can see there are 2 of these forming the pyramid like this. So what we are forming here, we want to look at the shape of what you are seeing. We call this as this has formed what we call a trigonal bipyramidal. Trigonal bipyramidal. So this is the shape of something like this. Anytime you have a molecule like this, we call it a trigonal bipyramidal. Alright? So we can give a typical example and demonstrate that quickly. Let me demonstrate this quickly. So you know the shape now. It's forming trigonal bipyramidal. Let's have an example like PCl5. PCl5, you have to first of all look at the central atom, which is phosphorus. Phosphorus is having atomic number 15. So let's try the configuration: 1s2, 2s2, 2p6, 3s2, 3p, let me see, 3, right?
Yeah.
So this is 10, 12, 30, 40, 50. So this is the electronic configuration of phosphorus. Having done this, this is the ground state. We said that we use the excitation or the excited state. So all these are not important. We only use the outermost electrons. So the outermost electron for this, we want to excite this. We are going to have this 3s, 3x, have the 3p. So let's look at the number of electrons here. We have 2 electrons in this, and then there are 3 electrons here. Now, there is the need to excite an electron. But the question is, if you try exciting an electron by promoting it from here to here, these ones are already full. They are singly full. When you bring this, it means they cannot undergo mixing. So they will not prefer to be added to this. If you are promoting it here, you cannot promote it to the p orbital. But you have to promote it to the next energy level, which is empty. These ones are occupied. So that will have to there will be an introduction of the d orbital, and this d orbital is also a indigenous orbital with 5 subdivisions. 1, 2, 3, 4, 5. So this is a d orbital, d1 to d5. So we are promoting this electron from this energy level all the way here. So this is what you get. So let's rewrite this. 3s is 1, 2. They are having single electrons. And then this d orbital is also degenerate. 1, 2, 3, 4, 5. Okay. So it will be occupied with this 1 electron like this. So these are 2px. Py is here, then this d1, and this is d1. So the d orbital has been occupied. So having done this, in sp3d, you have to mix an s orbital with 3p with a d orbital. That forms a sp3d orbital hybridization. So just like we did, let's quickly do that. Someone will ask, what is the bond angle of this? Yes, it is necessary to ask the bond angle. Here, there are 2 bond angles here. That's why we don't lay emphasis on this so much. We have, let me draw it and I will explain. So we have phosphorus here.